Okay, hello everyone, welcome back. So in the previous class, we have provided you with the introduction to the two-parse algorithm. And we also introduced how to use the two-parse algorithm to implement many different operators, right? It has been demonstrated to be useful for the data with larger scale and compared with a small memory, right? And we also compare the different operators as well as their implementation details, the cost, requirements, and we also show you with a summary for the two-parse algorithm-based algorithms based on sorting, right? In this class, we will continue to discuss about this section on query processing, and we will introduce two other methods or algorithms we can use to dealing with different operators. The first one we plan to introduce here is called a hash-based algorithm with a two-parse. And we will introduce how to use this hash function to help us to design a two-parse algorithm to implement different operators. And besides this, we will also introduce some the algorithm based on the indexing state. In other words, for this kind of algorithm, we don't need to require any pass anymore. We have zero pass, and we directly use an index table to help us to implement the operators. Okay, so we will first introduce the two-parse algorithm based on the hash function. So the basic idea for the two-parse algorithm with the hash function is to partition a relation R into some buckets, and we can also load these buckets into the memory for processing. So we need to ensure the bucket size is approximately about BR divided by M. BR denotes the number of blocks of the memory R, right? This M denotes the blocks we can hold in the memory. And after we do the partition, of this data we have on the disk into buckets. For example, we have a relation R. It is stored, the data of the relation R is stored on the disk. So we have BR blocks, right? And we propose to partition this relation R into some buckets with bucket 1 until bucket n-1. So, and you can see when we have the relation R, right, we need to partition this relation R into buckets. We still need to read this relation R into the memory, right? So for the relation R, we have BR blocks, and we will read each block into the memory, and we design a hash function H. Given the inputs according to the hash function we design here, we can partition or we can assign a block to a certain bucket, right? Bucket 1 until bucket n-1. So we will assign a block to a bucket, and we need to decide which bucket we need to output. It's an input 2, right? So the memory we have M blocks, right? Besides output buffers, we store here n-1 out buffers, and we also have one buffer for the inputs, right? So therefore, we will consume M blocks in the memory. And we assign this input to a bucket according to our hash function, and then we can write this block to the bucket on the disk again. You can see we have one read and one write, right? And between them, we have to design this hash function very carefully according to our requirements. So this is the general idea for the hash function and all the hashing-based two-parse algorithms. So based on this hash function, we will be able to partition the relation into buckets, right? And we can also ensure that for each bucket, the size is approximately BR over M, right? Of course, for different buckets, the number of blocks we will store in them will be different. Some can be more, some can be less, right? However, here we have a requirement. We need to ensure we can store each of the bucket into the memory, because later on we have to load this bucket into the memory. Therefore, we have one constraint. We need to ensure that BR over M is no greater than M. We have assigned them to the buckets already. Later on, we will load them to the memory. We have this constraint here. BR over M is no greater than M. In other words, BR is no greater than M squared, which will be very similar to the constraint we showed before, right? Okay, so this is how to partition a relation into buckets. Later on, we will show you how to use this hash-based algorithm for implementing some operators.